Welcome back to Math Concepts. We are going to continue our discussion of probability. In particular, we're talking about ways to use counting principles and some tools related to the counting principles, like factorials, permutations, and combinations. So the key ideas that we'll discuss in this video are ways to use permutations to help solve counting problems. So let's jump right into an example right here. So let's say we have 7 tutors available to work, and 3 of them are juniors and 4 of them are seniors. And we want to assign these 7 tutors to work during the 7 hours that the math center is open. And I want to know how many different schedules are possible. Okay, let's look first at the case where there are no restrictions. Okay, so we have 7 people, and we have 7 spots. Okay, so we could just use the counting principles to do this here. 1, 2, 3, 4, 5, 6, 7. We have 7 spots. So first slot, that could go to any of the 7 tutors. Next slot has to be a different one. Okay, and here I'm pretending that the tutors can only work 1 hour each. Okay, so 7 times 6 times 5 times 4 times 3 times 2 times 1. If you look back at the last video, there's a shorthand way to write that. That's 7 factorial. I guess the other way you could do it is you could say that's a permutation of 7 things in 7 spots. Okay, so we can get our calculator to do that computation very quickly. Clear out that last computation. 7 factorial equals 5040. Okay, so there are 5040 ways to make this schedule. Note here that, of course, if you're making a schedule, order matters, right? If you're first on the schedule, you got to show up first thing. So let's look at this. This is the situation where we have a restriction on who can work when. Okay, the juniors are going to take the first 3 hours, and then the seniors are going to take the next 4 hours. Right? Because we set up here, the math center is open for 7 hours. Okay, so I could break this up like this. Okay, it's a 2-step process. I'll choose the order for the juniors to work, that's my first step, and then I'll choose the order for the seniors to work. Okay? So if we have 3 juniors and we're going to fit them into 3 spots, well, the number of ways to do that is 3 factorial. That's the number of ways to complete my first stage. If I've got 4 seniors and they have to fill in the remaining 4 spots, there are 4 factorial ways to do my second stage. Okay, so let me see here. Just going to use my calculator to do that computation. So 3 factorial is 3 times 2 times 1, that's 6. 4 factorial is 24. So we get 144 ways to fill out the schedule if we meet this condition. So it's a neat little situation where we have the tools of permutations or factorials being used in conjunction with the counting principle. I want to show you one more application of permutations. Okay, so the key idea from this example is being able to count rearrangements involving identical objects. Okay, I want you to consider the letters of my last name here. Okay, that's my last name. McNamara, M-C-N-A-M-A-R-A. I've got 1, 2, 3, 4, 5, 6, 7, 8 letters in my last name. And we're asking, how many ways could I scramble these letters? Okay, well let me just do one example of a scramble here. I'm going to scramble the letters of my last name. And that's my result. Now you might say, well, you didn't do anything. You didn't scramble any of the letters. They're all in their starting positions, but I did. This M went over here. And this one went over here. Okay, the C stayed in the same position, and the N stayed in the same position. All the A's moved around. They got totally changed up. This A moved over here. This one moved down there, and this one that was on the end moved to the start, and the R stayed in the same position. Okay, so that is an example of a situation where we are doing rearrangements, but some of the objects are identical. I've got two identical letters here, the two M's, and I've got three A's. All right, so how could we count the number of rearrangements? Well, this is what we have to do. Okay, we first treat it like everything was different. I got 8 letters. I'm going to rearrange the 8 letters in 8 spots. Okay, there's 8 factorial ways to rearrange 8 letters in 8 spots. But then I got to divide some things out, because some of these rearrangements end up looking the same. So what I need to do is I need to divide out the number of ways to rearrange the two M's in whatever 2 spots I choose for the M's, since they're identical. And there are 2 factorial ways to arrange 2 things in 2 spots. Then I got to deal with the A's. Once I choose where the A's are going to go, I got to divide out by the 3 factorial ways to rearrange the 3 A's in 3 spots. Okay, so let's do the computation here. So clear it out. 8 factorial. Okay, and that's 40,320. And now I'm just going to do this part in my head. 2 factorial is easy. 2 factorial is 2. 3 factorial is 6. So I got to take this number and divide by 12. So there are 3,360 ways to get a distinct rearrangement of the letters of my last name. Okay, so when you have identical objects, you need to do this division trick. So you need to figure out how many groups of identical objects do you have. Okay, the reason this 2 factorial is here is because I have 2 M's. The reason the 3 factorial is here is because I had 3 A's in my last name. If I had another set of identical letters, I would put that next part over here. Okay.